All right. Well, finally, I have somebody came here and they figured out how to do this class on Zoom. So I'm using the computer system in this class. So now this class will be live. So many of you who could not join the class for whatever reason, you could still be able to join wherever you are. And also I'm recording. So that means I will also post that on YouTube. So that you can go back and see if sometimes so a lot of times it's helpful to go back and see what I said at what point. Okay, well, this is lecture 7. This is week 4, and now we are going to start applying what we learned so far in the first 3 weeks, solving different types of engineering problems. So today is surface water. We are going to see we are going to solve problems related to surface water. You already did to some extent in your mass balance problem, but I'm going to reiterate some of them and give some more specific problems. So few announcement. Homework 3 is due Wednesday. As you know, I'm very flexible when it comes to homework. If you for any reason cannot submit at certain days and you need extra time, always ask. What I don't like is you don't submit, okay? Because that doesn't help anybody, because then I have to give 0 at some point. After 1 week, I have to give 0, and that really affects your grade. So always submit your homework. If you are late for any reason, don't afraid to ask, because I'm looking for you to try, okay? And then you should try not yourself. You should try as a group, because you learn from each other a lot. So if you have struggled for doing homework, always reach out to your friends. Okay, that's very important. It's a teamwork at the end of the day, because a lot of environmental engineering problems can be solved by one person. You need that team activities when you work in any engineering firm. So this is also part of your training, to reach out to people and help each other solving a problem. I'll also post solution 1 and 2. The reason I didn't post it, I already had the solutions and I gave it to the grader. But I'm waiting for 2 students who had, for health reason, didn't submit their homework. They submitted 1, but the number 2. So I want, as soon as they submit, within the next 2 days, I'll release the solutions. Once I release the solution, then I don't accept any more homework. So that's why I sometimes delayed to accommodate that 1 student. All right, so again, if you have difficulty in solving any questions, you have many choices to get that clarifications. You have 4 discussion sessions, and then also you have office hour with me. You have 2 classes. You can always ask before, not before, mostly after the class. While wait around, if you have any question, I always can help after the class. And then also I have office hour, and if you can make to office hour or any of the, and then TA has also 2 office hours. Okay, so there are many chances per week for you to actually get help from us. So we are really counting on you that you will take advantage of all that and make sure that you submit your homework, which is near to perfect. Because we normally homework you should get 100%, because we ask you to get help. And any of you who have come to office hour, as you know, I don't really, I not give the solution, but I work with all of you to get to the correct approach. So after office hour, you know how to solve it. It's not really whatever question you ask. All right, so today we are going to learn about surface water, and that's on chapter, I think it's not chapter 5, so I have to, this is from the old textbook. So this is chapter 1 or 2. So I'll check those. It's already uploaded. If you go to CCLE, you'll see the PDF, which has materials for this week of class. All right, so how we are doing as part of the syllabus. So this is a progress. In the very first week, we learned a little bit about chemistry background. The second week, we learned a little bit more about mass balance concept, and we have been solving questions on that for a while. And the week 3, we learned about biology as well as risk. That's very like mostly quiz related questions, not long questions. And this week we are going to learn about surface water and groundwater. Okay, so these are the two aspects you are going to learn this week. And next week we'll learn about drinking water treatment design. So everything we cover in the first 5 weeks will be in the midterm, which is on week 7. So we give you that week 6 for you to catch up with anything you didn't understand, so that you are ready on week 7 to take the midterms. And midterms is again take home, like any exams here, and you will have very specific durations in 24 hours. So once you open the exams, you have, I have to check now what time it, like 3 hours or 2 hours. And so mostly the time should not be a limit, but many of you, if you ask for extra time through CIE, you get that. Okay, I don't really, anybody ask extra time through the official channel, we give you that. But time should not be factored based on the statistics from last 5 years. Okay, so so one way you can improve your timing is by solving the homework many times before the midterm, so you know how to solve the homework itself. And the questions in midterms are very similar to homework. So if you have done it, you should not have too much difficulties. And homework 3, I know the last 2 questions, there is a term called potency factor, and we didn't really cover that in the last class. So I just want to briefly say what is that, because many of you can go back and read the book, that particular sections, and understand it, but still I want to say it. So if you know risk, now we talk about how much pollutants you can get exposed to before a disease is developed or the effect is being felt. And for cancer, we always assume that the risk is non-zero, even you exposed to one chemical. Okay, so that non-zero factor is very important. But most of the time when we design the experiment or we calculate the risk, we do experiments. We give some dose of chemicals to rat or any species that we are testing. And those concentration that we use is very high, because you don't want to do experiment for many years. You want to finish the experiment within few weeks or a month, not beyond that. But if you give very low dose of concentrations, the rat will not develop the disease. So that means your experiment is not sufficient to actually calculate the risk. So oftentimes the concentration given is unrealistically high. And so that means how do you extrapolate what happens to the rat at the high concentration to the concentration at the low dose? And not only that, how do you even extrapolate that to human? Because human is not same as rat, right? So there are two conversions that we have to account for it. But how you convert what happens in the rat to human is a very different story. That's more biology, and we are not going to cover it. But how do you extrapolate the result at high concentration to very low concentration, which is what affects us, because we are not exposed to cancer-causing chemical at very, very high concentrations. So to do that, you have to scale it, the results. So as you can see in this figure, you have data until here. Okay, that's the lowest concentration data. But what you are looking for is here, because the exposure of concentration within this range, very low concentrations. You can't do the experiment at that low range. So somehow you have to extrapolate what happens at that very first low concentration that you can do experimentally to all the way here. To do that, you have to do modeling. Okay, so there are some models that has to fit that points and then extrapolate, and that whatever line you get, you have to calculate the slope of that line at that very low concentrations. And that slope is potency factor, means what is the potential for things to be developed. So potency factor is basically if you extrapolate that, if you see in these pictures, you extrapolate that one, and if you see in the bottom graph, is basically the zoom version of that graph. Okay, whatever that slope, that means you are saying if you expose to very low concentration, there is some non-zero risk, and that's linear. Okay. So potency factor is basically the slope at the very low concentration, near zero. And you see that y-axis is always incremental lifetime cancer risk, and x-axis is the amount of dose, okay, that's given to the species. In this case, for us, okay, because we are extrapolating for human. So chronic daily intakes is basically how much amount of dose you are receiving per day. For instance, if you are exposed to, every day you are exposed to gasoline, because if you, the moment you are filling your car with gas, you are inhaling some of those gas, right? Gasoline, continuous exposure of gasoline, it's not going to cause cancer for sure, but it's also cause different disease, right? So that's how you can calculate, if you fill the gas tanks throughout your lifetime, how much you are actually exposed to, and does it make any disease? That's how you can calculate. So this potency factor, as you can see, is determined experimentally using model. So this is a number that's given to you, okay? So many of the problems that you see in the question in homework, the potency factor is you have to get that number from the book, and that's from the book table 9. Okay, table 9, we list different chemicals: arsenic, benzene. Benzene is what you found in your gasoline. As you can see, that also cause cancers. Okay, but very high concentration. So you calculate that amount it cause cancer is not something you'll expose to in your lifetime if you're doing normal activities. But if somebody just, let's say, work in gasoline tank for whatever reasons and really putting his nose inside it all the time, obviously that's not the right thing to do. That can cause cancers. So these are the list of chemicals. It gives you different group of carcinogen, A, B, that's classifications. And then it says potency factor. As you can see, there are two potency factors, because it depends on how you are exposed to the pollutants. One is through oral route, means if you eat it. Another is through inhalation route, if you inhale that particular pollutants. For benzene, you are mostly inhaling, you are not eating those. But what if it is in the food? It can be. What if in your fish? For instance, if you see, let's say, look for another one. Cadmium, that's a metal. It's very rarely you inhale that cadmium by atmosphere, but metals are usually present in soil. So that can get into the foods, so that means most likely you will get that through oral route sometimes. But as you see, it doesn't really say what's the number through oral route. That means this cadmium bound to something other organics. That's how it get into inhaling through our through nose. So this is the number. So bottom line is you get this number, and that's how you are going to put that in your equations. So potency factor that's given is basically incremental lifetime risk divided by chronic daily intake rates. Okay, that's the number equation you got. So that means you can calculate incremental lifetime cancer risk. That's something we are concerned about. We want to know how much risk we have. That's what usually you will calculate. So that one is basically potency factor, which is given to you, times chronic daily intake, how much you are exposed daily. That's the one problem will give in certain way, and you have to estimate that. Potency factor is, from the table, you multiply, that's the risk you will calculate. So in the example problems, you'll see how it is being used. And then that's how you can use for the homework problems. Okay. So look at this particular 2-page so that you can understand a little bit more. And that's how you can use to solve the last 2 questions on homework. So what I'm going to do, I'm going to use this just the very first bit, because this is very similar to, this is example problem in the book. Okay. So that you know how to solve it. When a drinking water is disinfected with chlorine, an undesired byproduct chloroform may be formed. So the chemical you are interested in is chloroform. Suppose 70 kilogram person drinks 2 liters of water every day for 70 years with a chloroform concentration of 0.1 milligram per liter in drinking water. Okay, so that's the drinking water standard. You can't exceed that amount. So that means you are assuming this 70 kg person has been drinking their water for whole lifetime, 70 years. What's the risk of developing cancer for that person? So that's the questionnaire. Everything else is basically simple calculation. You can check it, but let's see how you can solve it. That's basically given to you in the similar homework questions. So as you can see, you know the chemical, and that means the chemical is chloroform. So your first goal is to find out the potential factors for that chloroform. And it says you are drinking, you are not inhaling. Chloroform can be also volatile, but the mode of exposure is through drinking water. So it's oral. So potential factor by oral route is, if you look at the chloroform, so that's here. As you can see, through oral route, the potential factor is 6.1 times 10 to the power minus 3. And pay attention to the unit. There is a unit on the top. That means it says milligram of chloroform for kilogram of body mass per day that you can expose to, or the potential factor. So I'm going to write that 6.1 milligram of chloroform for kilograms of body mass per day. That's the potential factors. Now your goal is to calculate what is the CDI, how much daily intakes you are receiving by chloroform. So as you can see, that person drink 2 liters of water, right? So you know the concentration of chloroform in. So let's start writing those. So concentration is 0.1 milligram of chloroform per liter of water, and that person is drinking 2 liters water per day. So chronic daily intakes. So daily intakes means how much amount you receive per day. If you do that one, so it become 2 multiply 0.1. So that means you are receiving or drinking 0.2 milligram of chloroform per day. So now that's the CDI, okay? Chronic daily intakes. And then, hold on, so CDI, that's right. So as you see, this is the reason I want to go back to these equations. This equation account for how much total amount of chloroform you can receive for 70 years of lifetime. Okay, and then also per body weight, because if a person is heavy, obviously the toxicity will be, you need a lot more amount to cause the effect. So if you write CDI there, so let's use that equations. Okay, so CDI, I'm going to write it again, 0.1 milligram per liter. So if you see that equation, intake rate, liter per day, so that's 2 liter per day, intake rate times exposure, how many days in life, you know? So well, that's something, you know, we assume that that person has been drinking for all the time in life. If you says 5 days a week, or it says whatever it is, so let's say that's not, so whole life it's receiving. Body weight, that's 70 kg. And then how many years he has been receiving? 70 years for life. Then 365 days for year. So now if you go get that one, you get CDI, then multiply to your this value, you'll get the risk. Okay, something will be very small, like 16 per million or something like that, 17 or 16 if I remember the examples. So most times, cancer risk is always calculate how many millions of people, in millions of people, how many will develop that cancer. So even a 1% develop in a million, that's a risk. Okay, so because a cancer, people are more stringent about it. So when you get a very small number, that's actually true. Okay, so check the example so that you see all the steps that I skipped. Okay, any question? Again, another, this is where we skip this one. I didn't read the question how many years that person has been exposed to, because for instance, when you are a baby, you are not drinking the water, like so maybe not you are start drinking that water from age 20, okay, whatever number, so you can account for that there. Okay, how many days you have exposed to. So that's basically you can see over here. If your next question, when this is calculated, it says this person is inhaling air, this concentration of that particular pollutants, and that person is inhaling 20 cubic meters of air per day, and that person is working 5 days a week in that particular environment, which is toxic. So that means 5 days a week is the exposure. And then, for a year, how many weeks in a year? Roughly 50 weeks. And that person has been working 25 years in that locations. So that's how you can calculate the entire risk from the lifetime. Okay. And so this is just example. So once the number is given, you can calculate this value. So again, check the homework questions, compare with this example so that you can see how to do those. This is very simple questions. This is another question, example 4 and 5. So if you do example 4 and 5 and 2 and 3, you know how to solve those last two questions. In fact, the question I gave you is much simpler than this example question given to you. So having said that, so you should be able to solve all questions on your homework, because other 3 questions are related to mass balance. You have been doing that before. It's the same concept. But if you have any difficulty, come to office hour tomorrow. Also check with the TA during their discussion session, their office hour, so that you should be able to solve it. Okay. So again, it's due on Wednesday midnight. Try to submit by then, but if you need extension, any of you ask. All right, so that's all for the questions related to homework. Okay. Now today's topic is first, we had quiz. All of you attended that quiz, so I'm very happy that nobody missed the quiz, because that's really, I can change because the solution is released the moment the quiz is end. Okay, so you can't have another quiz if you missed it. Okay, so there is no retaking quiz if you missed by any chance. But if you let me know ahead of time, so I don't release the solutions. I have to always turn off my phone, but today I forgot with all the excitement about Zoom being working. So let me airplane mode. All right, so that quiz, I'll share the solutions. But most importantly, today we are going to learn about surface water. So this is you can see the solution quiz, that's immediately graded by it automatically, so you can see. So the mean is 92%. So most of you got more than 9 out of 10. And the distribution is this. As you can see, majority of the students got more than 9, but even you receive less point, it's not end of the world. Many quizzes and 2 more quiz, and midterms, final, even you score 5 years, it's not going to end of the world. Just keep doing well in all rest of things, you still can get A. Okay. You can do calculations by default. Now, if you receive 5, what will happen? Not much. But if you continue to lose point in everything, it just add up. All right. So any question on quiz? All right. So next quiz is week 6, if I'm not mistaken, because every 3 weeks you have a quiz, and midterms is week 7. So those 2 quiz are going to help you solve the short question on the midterms. Okay, the very short questions in the first questions will be similar to quiz, but unlike quiz where they will not give in multiple choice there, you have to actually work it out. Okay. All right, surface water. Now that's the main goal of today's class. When we talk about surface water, is what we see on the Earth's surface. That could be pond, lake, river, ocean, all that counts as surface water. But for this class, we are mostly interested in fresh water, not ocean water, because that's what we need for drinking. That's what we use for daily life. As you can see, we are middle of drought in California. So one of the biggest challenges is how to know how much water we have and how do you conserve that surface water, because many of the water that we need are actually coming from reservoir. And you can see photos of reservoir drying down. That's because you don't receive enough water by rain or snow to replenish them. So one of the challenges is to calculate or estimate how much water we have per day, per year. That we can say, okay, this is the total inventory of water. So very first thing you have to do is learn how to calculate the amount of water in a reservoir. On the other side of it, if you have too much water, you can also cause this kind of issues like dam failure. Okay, so if you have too much water, it's going to flood. So this is one of the, in 2005, there is too much rain that time. It's in 2016 that you have so much water that that particular dam overflow. Okay, that spillway overflow, and that was a risk of entire dam to collapse. But luckily, it didn't happen. But if you know how much water you are going to receive, you can release that water beforehand, right? So that's another challenge of managing drought or flooding. So for that reason, your goal is to calculate how much water we can have in a reservoir because of all the input and output. So that's what we talk about hydrologic cycle. Hydrologic cycle means water is being transported from the surface, become vapor, went to atmosphere, then it falls as a rainfall. Some of the rainfall, the water goes into percolate into groundwater. Some of them evaporate back. Some of them will back to atmosphere through plants. There are many other processes that are happening. So if you account for all these things, it's a cycle. All the water is being turned over in and out. And so if you calculate where things are coming, then you can able to calculate how much water at particular locations. So this is again mass balance. So we did mass balance for lake before. If you remember, we already solved a question. Change in volume of a lake for time is all amount of flow coming in minus all amount of flow going out. Okay. This is something we have done it before. So this is, I'm reiterating again. As I said, you have learned everything you can in terms of the principle of the fundamental science. Now you are applying. So there is no new concept, just a new term. Okay. So change in storage, any lake over time, you can calculate by accounting for every flow coming in and out. The reason there is no reaction is because water is not reacted out or being totally destroyed unless, even how do you destroy water? You don't destroy water to oxygen and hydrogen. That's very small amount of water that goes split into those. But most of the time it changes the phase. Some of them become ice or some of them become atmospheric vapor. But you account for that in the flow. The evaporation is part of the flow. So there is no reactions. Okay. So now you can use that equations to solve any questions. So now let's see, you have many terms here. So I'm going to go over one by one. So you have a lake. This is all terms that possible. So Q in is basically water the flow rate coming in as a surface runoff. Every time it rains, there are some water coming in. Thus the stream flows into the lake. Then some stream, if leaving the system, that's Q out. Okay. Then another time, if you have rainfall directly falling onto the lake, that's the rainfall. So that's precipitations. And then if the precipitation happens also upstream, and that become a runoff. So this is stream, okay. That runoff, let's say the precipitation happen here and then become a runoff, that's R prime. And then also some of the rainfall percolate into ground and become a seepage, where underground the water is feeding into the lake. So you don't see that. So that's seepage coming from bottom through the soil. So these are the things that's coming in. What's leaving the system? You know there is a stream water going out. And then you can also think that evaporation can evaporate some of the water. So that's evaporation, E. And if you have plants on it, they can also take some of the water from the lake and transfer into the atmosphere, because that's how the plant survives. So that's ET. That's because of plant. Okay. Again, you just have to check whether it's coming out or leaving the system. And then the lake can also lose some water by seepage through underground in the soil. So that's I out. There could be many other things. And then density of water. So as you can see, it's a mass balance. So you have account for volume. If you multiply volume times density, you get the mass. That's why there is a density term. And because if you assume density is constant, then you can also remove it from the system. So again, this is mass accumulation rate, dm by dt is basically volume time density is mass, okay, and density is out, dv by dt, and this is basically density times all the volume over time is flow rate. Okay, so that's the Q's. So what mean I means every flow rate possible. Okay, and this could be all of them. And in many problems, you may not give in everything. That means you can assume those zero. Okay. If it's not given, you don't have to account for that. So if you know this one, you can calculate how much total weight of water that coming into the system. Okay. And if you divide by density, you calculate how much volume. Okay. And that's what normally you are interested in. Now you can see many of these things is very hard to measure as a volume. For instance, precipitation. How do you know the volume? Because a lot of times precipitation, if you remember, it says 2 inches of rainfall. It doesn't say how many gallons of rainfall, right? So it says 2 inch. What that means is 2 inches of rainfall is happening through the entire area. So if you multiply area times inch, which is the depth, you get the total volume. So many of these factor is actually given, anything related to surface area, it given as a length scale, not the volume scale. For instance, evaporation, it says 1 inch of evaporations through the entire area. So that means in the volume, if you know the volume or the flow rate, the same as area times length, the height. Okay, so that's a G. Area time velocity or the flux. So normally you can turn that volume to a flux, which is inch per hour or inch per day or millimeters per day. So that's why many of these units, when you change to precipitations, this is what I is a seepage. Seepage is going through the ground, so that's also area. Evaporation, it happens throughout the entire area, so that's all of those things are given as a length. Okay, so if it is given, you have to multiply that area. Okay, so if you account for those things, you can also calculate. So check out the units. If the units are given, you will know exactly what to use, whether you should use area or not. If it's given as a volume per liter or volume per time, then you don't need area. But most of the time it won't for those factors, because it's very difficult to measure the total volume. They calculate mean flux. So let's solve example problem. That way you know how to solve it, this kind of questions. So this will be part of the homework that's coming next. Okay. Clear Lake has a surface area of 708,000 square meter. Okay, so that's the area. Area is given means I'm not going to give you the volume for many of them. Okay. In May, the bubbling brook flows. So that's basically a stream flows into the lake at an average rate of 1.5 meter cube per second. So that's basically stream flow rate. So this one is Q in. Then there's a river that flows out of the lake on average of 1.2 cubic meter per second. So there is a flows out. The evaporation rate was measured as 14 centimeter per month. So here is the things. So this is evaporation rate. So that's E. And if you see the dimension, it says centimeter per month. Okay, so length over time. So it doesn't say the volume. That means to change to volume, you have to multiply the area, because evaporation happens throughout the entire area. A total 22.5 centimeter of precipitation fell in May. Precipitation is rainfall. So that's basically what you write, that precipitation P. Okay, so P is coming in. Evaporation is leaving. Q in is coming in. Q out is leaving. Okay. Seepage losses are negligible. So that means it says that you don't have to account for anything lost because of water that moving underground. Okay, you can say 0. The average depth in lake on May 1st is 19 meters. So it's saying that the amount of water that in the lake is, the depth is 19 meters. What was the average depth on 30th May? So basically, in 1 month, how much water you receive. If you know how much water you receive, you can calculate how much the water will rise, because you know the total area. If you know the total volume, so basically it's asking what is the height that will rise. Okay. And height rise is basically volume divided by area. Volume of amount of water that receive, volume of water gain or lost. That's how it's going to drop. If it is lost, then it's obviously it's going to drop, divided by area of lake. So all you are calculating is the amount of volume gained or lost. Okay. Net volume. So basically you are calculating dV over dt, whereas this goes here, and dt is 1 month. Amount of time to gain that volume or lose that volume is a month. Okay. So that's basically, if you use that equation, previous equation, everything coming in is, let's write this one. So I'm going to write it here. Okay. So this is already written here. Everything I put here. clear lake, Q in, coming in, Q out. Then you have evaporation, then you have precipitations. Everything else you can ignore because it doesn't give any numbers. So if you write mass balance equations, dV by dt is sum of Q in minus Q out. So what's coming in here? One is precipitation, another is Q in. Okay, so those two are coming in. So if you write Q in plus precipitations, again, precipitation, the unit is not same as flow rate. So that means you have to multiply times area. Okay, so that's all coming in. What leaving the system is Q out in the stream minus plus evaporations. Evaporations, again, if you see the unit is length over time, you have to multiply times area of the lake systems to have the same unit. All right, so let's write this one. Q in is 1.5 meter cube per second. And then again, it's for 1 month, right? So if you see this is a per month, so another way to write is because I'm calculating volume, so this is dt times this whole thing. So if I write this one, so this is 1 month, which is basically 30 days. So I'm just going to write it here, 30 days, so that you know. Then you have to change to day, like the flow rate has to be in per day. So 1 month, how many days, how many seconds? Let's write it. So 1 month is 30 days. Then 1 day is 24 hours. And 1 hour is 60 minutes. Each minute is 60 seconds. So that's Q in. That's the amount of flow rate or the volume of water coming in per month. Precipitations, how much is given? 22.5 centimeter per month. So this is, hold on. So this is actually in days. So I don't have to write it as a day. Because already account for in days, not month. Let me do one thing, so just so that I don't really make too much changes. You already wrote all those things. So 1 month. This one is 1 month. That way I'm changing to everything per month. All right, so that's centimeter, but then you know that the unit is in meter. The first thing you have to do is 100 centimeter is 1 meter. So you change to meter. Now times area. Area is given how much? 708,000 meters square. So that's the second term. Okay, so now if you see this unit become meter cube per month. Minus the next one is 1.25, again the same way. So we can say 1.25 meter cube per second times, I'm just going to write that same thing, 24, 60 times 60 second. And then minus evaporation is 14 centimeter per month. Again, same thing, 1 meter is 100 centimeter times 70800 meters square. So if you put that value, you get the volume, amount of volume of water that received by the lake. Okay, and then if you see how much height is changed, it's dV over area. You know the area, which is 70800 meters square, and this volume would be in whatever those things you got here in meter cube per, get in meter cube because month cancel. So the answer will be in meter. So in the exam, if you just write this way and say that this is what number over dV is here in meter cube, and the answer will be in whatever that number in meter. If it's negative, that means it's decreasing, the height is decreasing. If it's positive, then height is increasing. Okay. In the exam, you'll get full points by just showing that calculations. Any question? Is this the same question or what? This looks very similar. It has the same surface area. No, actually it is not the same question. Okay, but if it's the same concept, okay, so it's given, it just says when you receive water, when you don't, because it doesn't rain every day, right? It doesn't have flow rate every day. So there are some days it doesn't have anything, so you have to account for those times. So solve the example problem 2 by yourself so that you become familiar how to solve this question. It's the same thing, just put the equations, plug all this value, and you should be able to answer the numbers. And this is exactly what people do to calculate how much water we have in California for drought, or how much water we receive in LA and how much we should export or import. So this is it's a very simple thing, you know, that people use for all the complex calculations. But in nature, it's not really the parameter you receive is not always constant. For instance, its precipitation change over time. The flow rate itself is not constant, so things change over time. So you have to account for all those factors. When you do, it becomes bigger and bigger calculations that's done by computer. Okay, but it's the same question. That simple differential equations, this one can predict whether we are going to be in drought or not, or whether we have enough water or not. Okay. All right, so next thing we are going to talk about is surface water quality. So we talk about quantity, means we learn how much we have water. But next thing is how much of those water is actually clean, because we can't use polluted water. It doesn't matter how much water we have, because we have lots of water in LA through ocean. You can, I mean, ocean is right near us, we can get all of them, but it's so salty we can't use it, right? So same way, for water quality, it's very important to know that whether the water we have is actually usable or not. What determines that is actually the pollutant in it. So for instance, this particular video, let's see if it works. Maybe the volume would not work.
Prior to the late 1960s, there was no federal legislation to protect the environment. A number of events led to a shift in the American consciousness.
The sound is pretty bad. But point is, I want to show that, let's see the picture. Okay, oops. It's very hard. The quality is pretty bad. Just trust me, this is fire. Okay. So this was so polluted that the entire river was catching fire in 1960s. So many times that it caught fire that they can't. It's a real risk. The reason is before 1970s, people were dumping all their waste into river. There was no regulations. So that particular river has lots of industry on the side. So they dump all the woods, dump all the wastewater, dump everything they can. Really, there is no regulations of what you cannot dump. So that's why it is so polluted, mostly because of these organics that fish obviously will not survive. So check this video so that you can hear that one, because this kind of river, this is the reason why most likely the EPA was formed. EPA is the Environmental Protection Agency that formed in 1970. Ronald Reagan, Ronald Reagan or no, before that, Nixon. He's the one who founded EPA, Environmental Protection Agency, to make sure to oversee this kind of issues. So this is one of the big events that trigger that formation of that. So as you can see, surface water is critical. If you don't protect it, not just it catch fire, fish dies. Also, if you take a swim there, you will develop disease. So as you see, this is one example. Suddenly you can see that some places you see this news, all fishes are dying. Now, what's the reason? Most likely, for instance, right now, if you see the spill in Huntington Beach, a lot of fishes dies. Okay, and aquatic life die because a lot of oil. So if this happens, so why oil kill fishes? It's not necessarily oil directly kill fishes. They can survive still with oil. But what happens is fish need oxygen like we do. So when you have lots of organic, the bacteria itself will start degrading this oil, and they consume all the oxygen in water. So that means the oxygen concentration in water, if you have too much oil, is going to be so low that fish can't breathe it. It's like we no oxygen in the room. So that's exactly what happens why fish dies. If you have too much food for bacteria to consume it, and that's how they decrease the dissolved oxygen. So a lot of times a good surface water, the good indication of good quality surface water is oxygen concentrations. So a lot of times what they measure is how much dissolved oxygen in water. And what caused the dissolved oxygen to deplete is everything that can consume oxygen, because the bacteria are eating those food. Okay, so any organic that bacteria can digest is going to consume oxygen in water. So that's what we call biochemical oxygen demand. So in this class, you'll learn the concept of that, how to solve it. So those are the things we are going to learn after the break. So now it's 12:55. So let's have a break for 10 minutes. And then when we're back, we solve how to solve the same question that we already know. All right, so I'll see some chat window. If there's any question there, then I can answer. All right, so it looks like it's all working. So I'm going to pause the video for a second. All right, so if you have read your homework, which is due on Wednesday, if you see the first 2-3 questions, first question, second questions, and third questions are all surface water quality problems. If you see, there is a very first one, or even this one, basically saying that there is a treatment plant, it's discharging some pollutants, is going through LA River and then polluting ocean. So these are all surface water quality problems. So you can use the mass balance equation to solve any of them before even we get to surface water. So these questions are all surface water quality problems. So that means you know how to actually solve most of the problems throughout this year or throughout this quarter without even knowing the details about it, just using mass balance. What you are going to learn is the new terms, for instance, the different pollutant types, how to interpret them, right? So For instance, today you are going to learn about BOD. BOD is something, a term you may not have heard about it. And that's something we are going to learn. So when you solve these questions, you are just replacing the pollutant with the BOD. BOD is a term that's the expression of pollutant concentrations. Okay. So same thing for groundwater. There will be some extra terms somewhere here and there, but then we'll come back to again mass balance. Everything goes back to the mass balance. You design everything based on that. So that's why I say it's going to get easier in the sense that you don't have to learn new concept, but you learn different types of term that's new to you. Okay, so that's it. Okay, so as I said, surface water, what you're going to learn today is about BOD. What does that mean? We are going to learn. But in surface water, there are different types of pollutants. We learned that heavy metal is one pollutant, and chemicals, dissolved chemicals are also pollutants. We also learned that bacteria or pathogens could be a pollutant. There are many different kinds of pollutants, and their source are very important when you design how to solve or remove those pollutants. A lot of times, for instance, wastewater treatment plants, in that particular examples problems or the homework problem, wastewater treatment plant is the source of pollutant. So if you want to solve it, it's very easy to design a wastewater treatment plants that release less and less pollutant. But most of the time, the challenge are not because you have a point source. Sometimes you have source that you can't identify. For instance, nitrogen. You see eutrophications because of lots of nitrogen and phosphorus in water. And they come from different locations. For instance, if you apply fertilizer, those fertilizer end up in water. You have leaves, you have lots of the dead biomass, those release nutrients. So those come from all over the places, and those are non-point source, means you can't pinpoint what's the exact location of the source. And usually they came in storm water or runoff. Okay. So that's why it's very important to understand that many problems you can't solve if you don't know the source. Then you have to have a generic engineering solutions. So BOD is one such problem. So our BOD is not about just one type of pollutant, but it's a group of many pollutants. If the presence of those pollutants means bacteria will digest them and consume oxygen. So instead of looking for every pollutants, you are combining them to cause them BOD, biochemical oxygen demand. All it means that presence of those pollutants will cause the oxygen to deplete because bacteria is going to eat them. So it's called biochemical. So again, there are different pollutants. I just want to mention that every time you see different type of pollutant, the very top one is pathogens because that's toxic. Toxic in the sense you get immediately affected. It's acute toxicity. It means if you have, let's say, certain types of bacteria, it causes immediate diarrhea if you're exposed to those. So within a day, you get sick. But everything else, as you see, is not going to change very quickly. So effect is more slow process. One of the things you see, it says oxygen depleting substance. Why is important? Because, as I said, dissolved oxygen concentration is same as oxygen for us. We breathe if we have oxygen. If we don't have oxygen in water, most of the aquatic life will die. Okay, so that's why it's very important to understand that how do you make sure the amount of oxygen in water is always in the healthy level. So that's what we're going to learn, and you are going to learn that many different pollutants can remove or deplete oxygen concentrations indirectly. As I said, I saw back the same example over here. You see this dead fish. The reason is there are many chemicals in water, and those chemicals are food for bacteria. And when they digest those chemicals, even though that chemical concentration will decrease, but the oxygen concentration also is going to decrease. Right? So those bacteria will consume those oxygen, they will die. So those biomass of bacteria will also become food. So eventually it will become so anoxic that the oxygen concentration is so low that fish will not breathe anything. So that's why you see these dead fish. Okay. So this is one of the bigger problem for any time you see dead fish in lake is because of these issues. So it's called dead zone. You see a lot of these nutrients that release from agricultures or urban environments. These nutrients will fertilize the entire lake. Fertilize means you have so much nutrients and organics that bacteria or the natural microorganism will just have a feast. And so they'll grow so much, you'll see the algae. And when the algae grow, algae produce biomass. Those biomass are made of carbon. And so when the algae die, those carbons will stay in water. And those excess carbon become food for bacteria. And so when those bacteria will eat those carbon, they will deplete the oxygen. So a lot of times, people say algae basically does photosynthesis. So that means you should increase oxygen concentration. Yes, as long as they don't die, right? So they have to, when the moment they die, those organic is going to become food for bacteria. So that's one of the reasons we have to come up with a term. It's called biochemical oxygen demand, where it predicts how much oxygen we'll have in water. So before even you do so, how do you know how much oxygen in water if you don't have any chemicals? So that depends on how much oxygen can dissolve from atmosphere to water. And that's predicted by a constant. It's called Henry law. Okay, Henry law means it's a ratio of concentration in air versus water or vice versa, because Henry law constant can be any ratio. It could be ratio of concentration in water to air or air to water. Just by looking at the unit, you can say what is that about. So those Henry law constant is basically a thermodynamic constant that determine how much oxygen going to be in water based on how much concentration of oxygen in atmosphere. And it turned out concentration of oxygen in atmosphere is constant. 21% of atmosphere is oxygen, right? So that means if you take a constant 1 cubic meter of air, 21% of that volume is oxygen. Okay, so if you know that concentration, you should be able to calculate how much concentration going to be in water. So as you see, the Henry constant is a unit of concentrations, the ratio of a concentration. So for this Henry law constant could have a different unit based on what unit used in oxygen concentrations. For instance, in air, concentration sometimes is expressed as partial pressure, because the amount of molecule it causes the partial pressure. So 1 atmospheric pressure means entire air, and 21% of that air is oxygen. That means oxygen exerts 21% of 1 atmospheric pressure. So that means the concentration of oxygen is 0.21 atmospheric pressure. So a lot of times concentration is also expressed in partial pressure. So as you see, if the concentration is expressed as partial pressure, which I just mentioned, 0.21 atmosphere, you can change that to mole per liter by just dividing this constant. It's called rate. R is gas constant, which is a specific constant. That number is given. T is temperature. So all it means that if you increase the temperature, the concentration is going to change, because the partial pressure is going to change. If you the air is going to expand. So that means concentration of stuffs depends on temperature. So concentration of pollutants or oxygen in water will depend on how much temperature you have in air or water. Okay, that's because of this. So now let's use this. So Henry constant of oxygen is always given. As you see over in this table, oxygen Henry constant is 769. The unit is hard to see over here, atmosphere divided by mole per liter. Okay, so this is basically the unit is given here, and then if you reverse that unit to opposite ratio, that number will change because you are changing what the ratio is. If it is a unit less constant, because if you put this value, express the concentration more per liter for both, the unit cancel out, so it becomes dimensionless Henry constant. That's over here. So anytime I give you Henry constant, if I do give you dimensionless, I tell you usually what the ratio is. I'll tell you which one is the numerator, which one is the denominator. But if I don't give anything and say that this, you can guess that. Because for instance, if the partial pressure by, so if the concentration of air in the numerator, the unit of concentration in air will be in the numerator, which is atmosphere, 1 atm. So as you see, atm is the numerator. That means this is air over water. If the atm is at the bottom, then means you know this is a different ratio. Why it is important? Because if you know Henry constant, you can calculate either of them. If you want, other is given. A lot of times our goal is to calculate concentration of oxygen in water, because that's what we want to design. So that's one is basically the Henry law constant and concentration in air. Air concentration is always given. Okay, so that's, I just told you, 21 atmospheric pressure, 21% of atmospheric pressure is oxygen concentration everywhere. Okay, unless the atmospheric pressure changes, which can happen if you climb on the mountain. If you climb on the mountain, the oxygen concentration decreases because atmospheric pressure decreases. That's why a lot of times people who run marathon or run practice for those kind of things, they go to Boulder, where I did my PhD, because it's a mile-high city. So 1 mile above the atmosphere, above the sea level. So the oxygen concentration is low there. So that means if you train there with a low concentration, your lung has to breathe a lot more to get the same thing, right? So that means you are going to be more efficient when you go to the sea level. So that's the reason people train in the high elevations. So that's the same reason if you are training for, let's say, bike race, many of the bike races are on mountain. If you are trained at the LA level and you go there, you will really breathe harder. Okay, so that's one of the reasons. All right, so let's calculate example. Now that you learned the concept, let's learn how to calculate total amount of oxygen that can dissolve in water at certain conditions. So the question is, what would be the saturation concentrations in moles per liter of oxygen in a river in winter when the air temperature is 0 degrees Celsius? So the temperature is given 0 degrees Celsius, that's 273, roughly 273 degree Kelvin. I think it's exact is 2.73.7 or something. What's the 0 means? I have to check. Henry law constant is given. So Henry law of constant is given 2.28 times 10 to the minus 3 mole. Now, obviously, it's not a dimensionless Henry constant. So who can say is this concentration of oxygen in water to air or air to water? Because Henry constant of oxygen is always concentration of oxygen in water to air or air to water, one of them, right? So based on this unit, what would be this one? Air on the numerator or denominator? You can see the unit. atm is the concentration of air, atmospheric pressure. So atm is on a denominator, right? So that means you can write this one, moles per liter divided by atm, right? So moles per liter is water, right? Moles per liter is the concentration of oxygen in water. So basically this is concentration in water divided by concentration in air. Okay, that's why the unit is. So when you write this, you can directly predict. So it says what is the concentration of oxygen in water. So concentration of oxygen in water is Henry law constant. So if this is given, all I'm asking is what's the concentration in water. So I'm asking what is this term means. Okay, the value. So constant, based on that equation, concentration of oxygen in water in moles per liter would be Henry law constant, which is already given to you, times oxygen concentration in air, which is 2.28 moles per liter ATM. What is the concentration of oxygen in air? You know that 21% of oxygen, 21% of atmosphere is oxygen. So 21% of the entire atmospheric pressure is caused by oxygen. So that means the concentration in partial pressure is 0.2821 atm. That's always constant, okay, unless the atmospheric pressure changes. And this is assuming sea level. If you go higher, then that one atmospheric pressure will decrease. So you have to account for that. The atmospheric pressure change with elevation. So if you multiply that, it's going to be 2.28 times 0.21, atmospheric cancel, minus 3 moles per liter, whatever that number is. Okay. So this is a typical quiz, not quiz question, typical short question in midterms. Okay. Can anybody calculate what that number is? 4.79 10 to the minus 4. So now this is important here. A lot of times if somebody says what is the concentration of oxygen, they never give moles per liter. They usually give milligram per oxygen per liter, and that's normally 9. So let's see how do you change that. You already know from the very first class, how do you change moles to milligram? Oxygen is 2 oxygen. So what's the molecular weight of oxygen gas? 1 oxygen is around how much? 16, right? So that's 16 grams. 1 oxygen, 2 oxygen, 2 times 60, so 32 gram per mole. Okay, based on molecular weight. So this is 1 oxygen atomic weight. There are two here. Okay, there's 2 molecules, or 2 oxygen in 1 molecules. So that will be 1 mole is 32 gram, and then 1 gram is 1000 milligram. Can somebody calculate what the number is? $4.79 times 32,000. Or another way to do is if you take the power out, so 4.79 times 3.2. Whatever that number is. How much? 15.3. So 15.3 milligram per liter oxygen. Normally the concentration, as you see in the previous slides, this is oxygen concentrations 0 to 14 typically. That means as you decrease the temperatures, the oxygen concentration is more and more in water. So that's why the range is, what you got is around 15. That's the maximum we can have. As you increase the temperature, the oxygen in water is going to diffuse out. Okay, and the solubility decreases in water because of that. All right, so now you learn Henry constant, how to use it to calculate concentration of oxygen or actually any gas in water, if you know oxygen concentrations. Now, all you learn is what's the maximum amount of oxygen that you can expect in water. But what you don't learn is that what amount of oxygen actually present in water. Because the true amount of oxygen in water depends on how much chemical in water. Because as I said, the bacteria itself will eat oxygen or breathe oxygen in, to digest the food that is the chemical present in water. So based on amount of chemical in water or biochemical oxygen demand, that's what we call as a group, you can predict how much oxygen remain in water after they eat those food. Okay, so it's, think of this way: if you enclose this entire room and you have amount of oxygen, and we breathe in oxygen because we are digesting our food, right? The cellular function. So because of that, so the biochemical oxygen demand is our food or our lifestyle. And so we have more people here, that means more biochemical oxygen demand, right? Because you are eating more and then we are breathing more because we are digesting. And so that's what's happening. So if you have lots of chemical, that means you need more oxygen to destroy those chemicals. And in fact, because of that process, your oxygen concentration will deplete unless there is a way to put back oxygen at certain rate. And what happens in water is when you have lots of chemical, the bacteria itself is consuming oxygen at certain rate. And if that rate is a lot higher than amount of oxygen that can diffuse from atmosphere into water, then obviously your concentration will decrease. And it got to a point where the concentration is so low that fish will die because constantly oxygen is getting into water from atmosphere. So you have to account for both. What's the rate at which oxygen is being get into water? How much oxygen is being consumed in water? So that's the basically what we are going to calculate in next few slides. So amount of oxygen required by microorganism to oxidize organic waste aerobically. The reason it's called aerobic because you are exposed to oxygen is called biochemical oxygen demand. Just burning anything in fire is chemical oxygen demand. Because if you just catch, let's say you burn this one of the wood, the oxygen will deplete because that carbon is turning into carbon dioxide. Those oxygen is coming from atmosphere. So that's called chemical oxygen demand. So every materials has a chemical oxygen demand. What we account for in water is basically biochemical oxygen demand because the bacteria or the microorganism has to digest. That's the reason if your materials cannot be digested by bacteria, even though there is a chemical oxygen demand, the oxygen concentration will not decrease. One of the example is if you store water in a plastic bottle, the oxygen concentration doesn't deplete, even though the container is made of carbon, because bacteria cannot digest that carbon. Otherwise, if you store all this water in plastic bottle, after a point, those plastic bottle is dissolved because bacteria will eat those. It doesn't happen. So that's the reason biochemical oxygen demand account for chemical that is digestible or usable by microorganism, not the food that they can digest. Things like wood chips, the big wood chips, they'll still break down slowly, but plastic is not going to consume oxygen. But if you put the leaves in water, the oxygen concentration will deplete because leaves are easy to digest. So again, there's two parts of oxygen. So if carbon, CO2, this is just source of carbon. That could be any chemicals, okay? So that could be any chemical. So this is called carbonaceous oxygen demand, okay? So this carbonaceous. But sometimes you may have also nitrogen, as you see that, if you think of protein, they're made of nitrogen and carbon. So those nitrogen also digested. Okay. So this is called nitrogenous oxygen demand. The example is ammonium. Ammonium is one of the fertilizers that nitrogen that we apply. So if you have lots of ammonium, they can also consume oxygen. So depending on where the oxygen is consumed, we can call it carbonaceous or nitrogenous. Why it is important? Because if you know the source, you can actually plan different types of solutions. For instance, if your oxygen concentration is depleting because you are applying too much fertilizer, you don't have to worry about carbon as a source. All you have to do is remove the fertilizer. A lot of times organic pollutants has both nitrogen and carbon. Okay, so what they do is they first break the carbon into carbon and nitrogen, and then they destroy nitrogen. Okay, so a lot of times for instance, protein, as I said, protein is carbon NH2, right? So first they break it down to carbon oxygen plus NH. So first thing microorganism does is break that nitrogen away as ammonium, and then they use that ammonium to consume more oxygen. So the very first one is carbonaceous oxygen demand. The next one is nitrogenous. So that means when you have a complex molecule, first they will start breaking carbon, and that's how the oxygen will deplete. And the next phase, it will start consuming all the nitrogen. Okay, that's what you see in wastewater treatment plant. That's why a lot of times the wastewater plant design, the nitrogen removal takes place later, not at the beginning. So these are the concepts you'll see more and more in a design actual treatment system. So again, a lot of times people confuse what is BOD, what is oxygen. They are opposite. Okay. If you have lots of BOD, think of there are chemicals. They are chemical, they are stuffs that can help lower the oxygen concentrations. If you have lots of those BOD or oxygen demand, that means there are a lot of chemicals there. Okay. So they are opposite. If you have too much oxygen, that means you don't have many BOD. There is not enough oxygen demand. Okay, or not enough chemicals. So they are opposite when it comes to concept. So this waste is BOD. And BOD mixed with oxygen, that's the reason it's called oxygen demand, because it requires oxygen to be destroyed as carbon dioxide. So all microorganisms in water or wastewater treatment plants or drinking water treatment plants take those waste, you aerate it, add oxygen into it by adding aerations, and then you produce carbon dioxide. Those energy is produced by microorganisms for use, and then you produce more biomass. So this is the equation that describes the wastewater treatment plant. So these chemicals, waste comes in wastewater treatment plants, you do aeration, that's why you supply oxygen, that's how it gets clean. This is the same process why stream water becomes clean as it moves on the rock. Because in the rock, when the stream moves, it mixes that allow oxygen to get into the stream water, and those extra oxygen helps the microorganisms to digest those any chemicals. So that's the natural process, how the stream gets clean as it moves on the mountain. So this is the same process we use in drinking water treatment plants to clean water. So that's the whole process of BOD. So now let's say how one of the question will be calculate how much amount of oxygen that can be consumed for a reactions, which you already did for redox reaction. If you remember in the very first week, I gave you redox equation with a glucose or sugar, and say it add oxygen and then see what's carbon, how much carbon dioxide coming in. That's this equation. This is the application of that equation now. Okay. So this is coming back again. So let's use that equation to calculate. So let's see this equation. What is the theoretical oxygen demand for 1 liter water containing 1.7 gram of ammonia and 18 gram of glucose based on the reaction given below? So first thing you have to check is this a reaction balanced? Because first thing you have to balance the reaction. I hope I balance it. Yes. These are all balanced reactions. There are 4 oxygens. There are 4 oxygen. You have 2 and 3 hydrogen. You have 3 hydrogen. You have 1 nitrogen, 1 nitrogen. So that's balanced. This is also balanced. The only thing that is not balanced is the charge. But you don't have to account for that now yet, because all you are saying is this reaction happens. Okay. So now if you see both reaction use oxygen. So this is your oxygen demand. How much oxygen is being demanded based on how much amount of ammonia or glucose is there. So based on this redox reaction, let's calculate. So BOD, so amount of ammonia is given is 1.7. Let's do the first one. 1.7 gram of ammonia per liter of water. So how much oxygen it can consume if you need this much ammonia? You know that 1 mole of ammonia requires 2 mole of oxygen. So they are related molar way. So first you have to change gram to moles. So what is the molecular weight of ammonia? Anybody? Nitrogen is 14, hydrogen is 1, so 17. So 17 gram of ammonia is 1 mole of ammonia. And you know that 1 mole of ammonia can consume how many moles of oxygen? Based on these reactions, 2. Okay, so 1 mole of ammonia is consuming 2 moles of oxygen. It says what is the oxygen demand in milligram per liter. Usually it says milligram per liter. So that means you have to change 1 mole of oxygen to gram per oxygen. So one mole of oxygen is 32 gram of oxygen. So that's the molecular weight of oxygen. 1 oxygen is 16, 2 oxygen is 32. And then 1 gram of oxygen is same as 1000 milligram of oxygen. So you can calculate how much oxygen, milligram of oxygen per liter. That's the BOD, just based on nitrogen. Okay. If you do the same thing for glucose, so let's calculate. So amount of glucose is 18 gram. 18 gram of, I'm just going to write glucose, G for glucose, so that way you know where the G come from. 3 gram of G per 1 liter. And you know that molecular weight of glucose is 180, is given here. So 180 gram of glucose is same as 1 mole of glucose. 1 mole of glucose, how many moles of oxygen is consumed by 1 mole of glucose? Based on the reaction over here. 6. Okay, so this that equation means 6 mole. 6 mole of oxygen. And then you just do the same thing. 1 mole of oxygen is same as 32 gram of oxygen. And 1 gram of oxygen is same as 1000 milligram of oxygen. So BOD, or amount of oxygen demand biochemically, is basically carbonate oxygen demand plus nitrogen oxygen demand. So that means O2 required because of glucose, because that's all carbon, plus O2 required for nitrogen in this case. Anybody who got the answer here? How much amount of oxygen required for ammonia? 1.7 times 2 times 32,000 divided by whatever the number is. 6,400. Whatever the next one. 19,200. Okay, so let's write that one. So that's going to be 19,200 plus 6400. So that will be 0046 milligram per liter. You don't have to write oxygen anymore because that's called oxygen demand, BOD. What? There is something wrong, right? Yes. How can I write something without mistake? Finally, so that's good. What is this? It's a 2 here. All right, so as you see, you guys already know how to solve this question. All you are doing is the context of BOD and COD. So that's BOD. Just know that there are different problems that I will explain before we leave this end this class, because next class will continue with that. First thing is, a lot of times you know what is theoretical oxygen demand means. If you plug in that stoichiometry equation, the redox equation, that's the theoretical. That's the maximum amount of oxygen. But what is ultimate? Ultimate means the actual amount of is being consumed, because bacteria are not very efficient. They are not going to use all of them. So ultimate is always going to be less or equal to theoretical. Okay, just because you put all of them doesn't mean that bacteria will digest all of them. They're not as efficient. Okay, after a point, they will not digest certain things. So ultimate is basically less than theoretical. Okay, so that's kind of a quiz question, where I'll say theoretical oxygen demand is less than ultimate. Obviously, that's a false statement. Okay, so that's the concept. You know why it is, where it's coming from. And how do you measure oxygen? The way people do measure oxygen is they take this bottle, give some bacteria, the bacteria that's used for seed, okay, and they give some nutrients for them to grow, because it's not that the chemicals they are going to consume, they also need micronutrients. So you add some nutrients, you measure the dissolved oxygen before and at the end. So the difference is the amount of oxygen they used in certain days. So a lot of times, so that means DO initial minus DO final, P is the dilution factor. If you dilute the wastewater, that sometimes the chemical is so much that you have to dilute. If you don't dilute, this become 1. So the point I want to say here is that this entire experiment, or the time it takes, is 5 days. So a lot of times if you go work in an engineering firm or wastewater treatment plant, they say this is the wastewater treatment plant, this is BOD 5. What does that mean? So they did this experiment for 5 days. Now here is a trick. Do you know why it is 5 days? Why not 1 day? Why not BOD 1, BOD 10? Why 5? It's very funny though when you heard the answer. It's not very scientific. It's more convenience. Yes, in a week you have 5 working days. Nobody want to work more than 5 days. Okay, so if you do on the Monday, by Friday you have to get the results, because you don't want to come in weekend. So that's the reason BOD 5 is used. And another good reason is if you have a lot of time, bacteria take some time to get used to start burning. It's like you're not active. So if you do 1 or 2 days, maybe bacteria has a lot of the chemicals there, but bacteria are not active yet. So you have to use at least some amount of time. But if you wait too long, a lot of times those bacteria grow so much that they also produce a lot of bacteria, and that become part of the BOD. So that's the reason that you can't wait for too long. You can't do too quickly. 5 days turn out to be 5 working days. So that's the reason BOD 5. So now you know how BOD 5 is related to the actual concentration of dissolved oxygen in materials. So next week, what you're going to learn is how to relate BOD 5 with BOD. Is basically, if you see this equation, this is DO, amount of DO before and after. The difference is same as the BOD demand, right? How much BOD 5 means how much BOD is consumed in 5 days. It's not the amount of BOD remain in water. What you measure in always is the amount of BOD in water. This is what is the amount of BOD consumed, already gone. So how do you relate those two equations? Is basically exponential equation, and we'll show you that. It's a first order decay constant, which you already learned it. We'll plug that equation. That means if you know the BOD, you can calculate BOD 5. If you know BOD 5, you can calculate BOD. So BOD 5 is basically, think of this way. I am asking you how much money you spent in 5 days. That's BOD 5. How much money left in your bank account is BOD. Okay, so that's basically what's remaining is BOD. BOD 5, anytime you see a subscript 5, that means the amount of BOD consumed in 5 days. So once you get used to this term, everything else is plugging in the equation. You already learned. Mass balance, replace concentration by BOD. Okay, not BOD 5. BOD 5 is things removed. BOD, actual BOD. So everything else, mass balance is given. So next class, in the very first half of the class, we'll learn how to use this concentration term to solve a mass balance problem that you already know. And we'll solve one of the questions that was in the midterms. Okay. So again, read the textbook so that you know the concept of BOD, and next class you'll just solve the same concept using an over and over. All right.